welcome Tobias Meier. So Tobias obtained his master's degree in physics at EPFL, and since September 2018, he's been a PhD student at the Center for Space and Habitability at the University of Bern under the supervision of Dr. Dan Bauer. So Tobias, I'll let you go ahead and get going.
Yeah, hi everyone, and thanks for the introduction, Joe. And yeah, thank you for having me and giving me the opportunity to present our work here. So I'm going to present you. So I'm mostly going to talk. So I'm going to talk about the interior dynamics of tidally locked super Earths, and I'm mostly going to focus on our recently published research about the hemispheric tectonics on super Earth LHS 3844b. And I'm also going to touch a little bit then on our future project about 55 Cancri. And yeah, so this project was made possible thanks to a collaboration between planetary scientists, astronomers, and geodynamicists. And yeah, to start with, I'd like to give a very brief introduction about planetary geodynamics. And so, of course, in exoplanet science, a question that is always quite important or very important is the question of habitability. And so what makes actually a planet habitable? And so usually what one defines for this as first criterion is this habitable zone, which defines the distance from the host star at which a planet, where a planet then is able to have liquid water on its surface. And this, of course, depends on the solar insolation from the host star. And then from that, one can calculate the distance or this zone, this habitable zone. And usually one determines this zone assuming that the planet has an atmosphere. So for the habitability, of course, the planet also needs to have an atmosphere. And this then can determine the temperature on the planet and also the temperature on the planet's surface. And for the planet also to be habitable, one would say that the planet needs, or the surface needs to be made out of rock, as also the mantle of the planet. And depending on the temperature that we have at the surface, which is determined by solar insolation and the atmosphere, then this mantle which is mostly rocky, solid, this temperature then can determine whether the mantle is convecting or not. And if this mantle is convecting, then we can, for example, have, as we can see here, cold material that subducts into the mantle towards the core. And the core can consist of an inner core, which is solid, and an outer core, which can be liquid. And if it is liquid, then it might also be convecting, which then could also possibly lead, because the core mostly consists of iron and nickel, could then possibly produce a magnetic field. And this magnetic field can then protect the planet and the atmosphere from solar radiation or cosmic rays. And so what is important here is that all these different components, they are all coupled together. So if the mantle is convecting and we have here plumes or downwellings, then this can lead to outgassing, which can alter the atmosphere, which then in turn again can change the temperature at the surface, which can again make the mantle more or less likely to be convecting, which again will change the outer core and the magnetic field. So everything is connected. And in this project and what I'm going to talk about now, we focus on this mid-region here, which is called the mantle, which is the region between the surface and the core mantle boundary, which is defined here as the boundary between the mantle and the core. But so how can we actually determine, so when we want to look into the interior of these planets, what's going on in there, like for example here, like cold material that subducts into the mantle, these downwellings and then upwellings, the hot material that will rise, how can we actually model that? And so what we want to model is the flow of rock inside the mantle. And as the name says, this rock is rocky and not really liquid. And so how can we actually model this flow? And so the thing is that on geological timescales, the rocks will behave as highly viscous, as a highly viscous fluid. And yeah, on geological timescales, which means that we have timescales of millions of years. And in that case, we can then use the fluid equations to model the flow of rock inside the mantle. And so just as a short summary, what these fluid equations are, we have, so to model this, we have the conservation of momentum, the conservation of mass, and the conservation of energy. And well, the conservation of momentum together with the conservation of mass are the Navier-Stokes equations. And here in the momentum equation, we have pressure gradients, we have stresses, we have density, gravity, and here on the right-hand side, we have the inertial forces. In our case, for modeling the interior dynamics inside the mantle, the inertial forces can be neglected, so this term will be 0. What is important, what is very important because this system is so highly viscous, are these viscous stresses inside the mantle, as opposed, for example, in atmospheric models or ocean models, where the system outside of the boundary layers can be treated as almost inviscid. And yeah, so here the second equation is the conservation of mass, which is the continuity equation. And the third equation is the conservation of energy, where we here have the change of temperature, the conduction term, and then we can add all different kinds of heat sources. So in this case, we can include we include adiabatic heating, viscous dissipation, or also just the heat that is generated inside the mantle, for example, from the decay of radioactive elements. And so all these equations together will then be solved numerically, and we do that with the code STAGYY by Paul Tackley. Oh yeah, here for the energy equation, Cp is the heat capacity, and here the thermal conductivity. Just also a note on viscosity, because I said like these viscous stresses, they are very important in our simulations. And how do we, so we do relate these, we can relate the stresses to strain, or which is like the deformation inside the mantle, how the material will deform. And so in simple Newtonian viscosity, this will be related by this relation. In our case, it will be a bit more complicated, but in the end, it's still viscosity that will relate stress and strain. And so therefore, we need an expression for how the viscosity changes in the mantle, because viscosity depends on temperature, which is here shown in the plot on the left, which is the initial temperature profile in the mantle. And viscosity also depends on the pressure. So E0 here, so this equation is an Arrhenius-like equation to model the viscosity inside the mantle, where E0 is the activation energy and V as a function of P is the activation volume. And so in our models, we assume 3 different regions where we have the upper mantle consisting of olivine. Then we have the mid-mantle, which consists of perovskite or bridgmanite. And then in the lower mantle, we have this high pressure phase of perovskite, which is post-perovskite. And so viscosity varies depending, so for all of these 3 different phases, we have different activation energies and activation volumes. Also, to say about whether a planet is now more likely or less likely to be convective, we can use the so-called Rayleigh number. So the Rayleigh number tells us how likely or how vigorously a system will be convecting, where rho is the density, g the gravitational acceleration, thermal expansion coefficient, and then delta T is the temperature drop across the mantle or the convective region, and d cube is now the domain depth, or the depth, in our case, the depth of the whole mantle. And eta here is the viscosity, and kappa is the thermal conductivity. So all these terms on the denominator will be the terms, the buoyancy that will drive convection, and on the denominator we have everything that will oppose convection. So the higher the thermal conductivity, the more likely the system will be conductive, and also the higher viscosity will oppose the convection. And so just from the Rayleigh number, if now we look at different super Earths, as here we have 55 Cancri E and LHS 3844b, where LHS 3844b has a radius of around 1.3 Earth radii, and 55 Cancri has a radius of around 1.9 Earth radii. And so just from the size, one would say that, okay, so this means that since the domain depth now will scale as cube, this will make the system more likely to be convective. But the answer is not that simple, because, as I've said before, viscosity varies as a function of temperature and pressure. And so since these planets are much bigger as Earth, then viscosity will also increase and therefore hinder convection. So just from the Rayleigh number alone, we cannot say if these planets are now more likely to be convective or not. And so we need simulations to find that out. And for these 2 planets, what is also very interesting is this delta T, so the temperature drop across the mantle, because for these planets, since they are, as you can see here, they have very short orbital periods, which makes them most likely to be tidally locked. And so therefore, which means that they always face the same side to its host star, which means that they can have a very strong temperature contrast between the day side and the night side of the planet. We focus our research mostly on LHS 3844b and 55 Cancri E, because for these 2 planets, the thermal phase curves have been observed. So for these planets, we know the longitudinal variation of the temperature. And for 55 Cancri, we can see that there are very high temperatures but still a very strong temperature contrast between the day side, which is around 2700 Kelvin, and the night side around 1400 Kelvin. And here we can also see on the thermal phase curve plot that there is a hotspot shift. So this means that there needs to be most likely some kind of atmosphere that redistributes the heat such that we can have this hotspot shift. So which means that the hottest point is not at the substellar point, it's a bit shifted. And on the other hand, the strong contrast between the day side and the night side, this would rather say, okay, there is probably not that good heat distribution. So for 55 Cancri, this is still a bit of a puzzle. On the other hand, for LHS 3844b, we have a day side temperature of around 1040 Kelvin and the night side temperature mostly consistent with 0 Kelvin. And so here you can see there is no hotspot shift. And so this means that in this case, this planet most likely doesn't have an atmosphere. And so for us, this makes it easier to actually model the interior dynamics of this planet, because now we can use directly the temperature from the temperature distribution from the thermal phase curve as a boundary condition on the surface in our simulations. And this is what we now do for LHS 3844b. We take as an input the day side temperatures and the night side temperatures on the surface as a boundary condition. So all our models are 2D solid state convection models. And we set the temperature at the core mantle boundary to be isothermal around 4500 Kelvin. And as said before, the temperatures at the substellar point and the night side are given by the thermal phase curve. And all our models are fully compressible models with the parameters from Tackley-et-al. 2013, where the parameters from there also give us the viscosity profile inside the mantle. And what we vary in our models are, on one side, the heating mode of the planet. So we have either basally heated models, which means that all the heat that we generate comes from within the core. And on the other hand, we also have models with mixed heating, where we have basal heating, but then also internal heating, which means that we generate heat everywhere inside the mantle that could come, for example, from the decay of radioactive elements. On the other hand, we also vary the strength of the lithosphere. So the lithosphere is like this uppermost rigid layer, and depending on how strong it is, it can break more easily or not. And we implement this by employing a plastic yielding criterion, which means that whenever the stresses exceed this plastic yielding criterion, the viscosity is reduced, and then the lithosphere is allowed to break and subduct into the mantle. So when this parameter is very low, we will have more cold material or subduction that goes into the deep mantle. And on the other hand, when this parameter is very high, so a very strong lithosphere, then we will have less, or we can even lock up the whole surface such that we only have a very rigid plate that doesn't move. And so I'm going to show you now the results for all these four end member case models. So when we have a weak lithosphere with basal heating, what we observe is that we have a rather uniform distribution of downwellings, which are here the cold, the blue shown in blue, the cold material that descends into the mantle, and a uniform distribution of upwellings as well, here shown in yellow red, which rises towards the surface. the downwellings are rather uniform distributed, but they are stronger on the night side because of the stronger temperature contrast on that side. We can also see this when you have a look at this evolutionary plot, where we show now the distribution of downwellings shown here in blue as a function of time, and the same for the upwellings shown here in red. And so here we see again that we have this uniform distribution of both upwellings and downwellings, but we don't really detect in our algorithm the downwellings on the day side because they are too weak. What happens now when we have, again, basal heating, but with a strong lithosphere? In this case, what we see is that we have this hemispheric tectonic regime where we now have a downwelling preferentially on the day side of the planet, and then upwellings that get pushed towards the night side of the planet. And there's also a backflow of cold material from the night side towards the day side that is accommodated in the upper mantle that you can see right now here. And we also see this pattern here on the evolutionary plot again, where we have these downwellings, these upwellings preferentially on the night side, and a strong downwelling preferentially on the day side. When we now add mixed heating, so internal heating to the models with basal heating, so now we have a mixed heating case with a weak lithosphere again. What we now see is that we have again a hemispheric tectonic regime, but now with downwellings preferentially on the night side, and the upwellings that get pushed towards the day side, which we can also see here again on the evolutionary plot. And last but not least, when we have a strong lithosphere with the mixed heating case, what we see is that we have now downwellings again preferentially on the day side, and upwellings that get pushed towards the night side of the planet, which we can see here also on the evolutionary plot. Also note that now the downwellings, they are much narrower and diffuse away very quickly, which is a direct consequence of the internal heating that we added. And now the mantle, and therefore the mantle is now much hotter, and the viscosity is much lower. It's also interesting now to have a look at the surface mobility of the lithosphere, which is, so the mobility is like a proxy for the surface velocity of the lithosphere. And so if the mobility is 0, we would recover a stagnant lit case, which is this rigid plate that locks up the planet. And as you can see, for all our models, we actually have always non-zero mobility. So we never actually reach a stagnant lit case, even for the strong lithosphere case. But this is a direct consequence of the fact that we always assume that we have a finite plastic yielding criterion, which makes the lithosphere mobile. And so to summarize the results for LHS 3844b, when we have a weak lithosphere with basal heating, we have this uniform distribution of upwellings and downwellings, with the downwellings being stronger on the night side. When we add mixed heating to that, we find a hemispheric tectonic regime with downwellings preferentially on the night side, and upwellings that get pushed towards the day side. For the strong lithosphere case, we recover a hemispheric tectonic regime for both cases, but now the hemispheric tectonic regime is reversed. We now have downwellings preferentially on the day side, and upwellings that get pushed towards the night side of the planet. So for 3 out of 4 of our cases, we recovered or we find this hemispheric tectonic regime, which is currently absent in our own solar system. And the question, of course, now is, can we actually detect any of these, or can we distinguish these different regimes, for example, through secondary features in the thermal phase curve? If, for example, we can link these upwellings to regions of enhanced outgassing or volcanism. And for this, we also just looked at what would the thermal phase curve, which is shown here on the plot on the left, how would this thermal phase curve be affected now if we just consider the heat flow that comes out from the mantle? And for the night side, the results are plotted here on the right-hand side. And you can see that temperatures would be affected by around 40 Kelvin or 25 Kelvin. And so, unfortunately, this is not something that current or near future observations could detect. But on the other hand, if these upwellings could be linked to regions of enhanced volcanism or something like that, then possibly these could generate melt, which then would lead to higher temperatures, which possibly could lead to a signal in the thermal phase curve. So now I would also like to talk briefly about 55 Cancri E, and where I have already introduced that the dayside temperature from the thermal phase curve in this case is around 2700 Kelvin, and for the night side it is around 1400 Kelvin. So the planet is now even bigger than LHS 3844b, around 1.9 Earth radii, but it's again on a very short, it again has a very short orbital period, which makes it very likely to be tidally locked. And so, yeah, these are the results from the thermal phase curve that I've already shown with this hotspot shift that we can see. And so this is still a puzzle whether the heat redistribution is now actually effective or not, because from the hotspot shift you would expect that the heat redistribution is effective, but from the strong contrast between the day side temperature and the night side temperature, we would actually expect that heat redistribution is not that effective. What also is more complicated now, that if we assume that this planet has an atmosphere, then we cannot directly use the temperature from the thermal phase curve as a boundary condition in our models. And so for this, we use the results from general circulation models from colleagues in Oxford who run these models of the atmosphere and then can give us the temperature at the surface for different compositions and optical depths of the atmosphere. And what is also important now, since the temperatures are so high, is that now we can potentially have a magma ocean on the planet's surface. So here are shown the solidus and the liquidus. And as you can see here, at least the day side would probably be molten. For the night side, it's not that clear, possibly not, or it could also be molten. And then we could have a magma ocean with a certain magma ocean depth in on the planet. And this complicates things a little bit, or quite a bit, because now the planetary mantle is not only solid, but it also has this liquid magma ocean on top of it. And the solid part, as before, behaves like this highly viscous fluid on geological timescales. So this we can model using a viscous flow model, which solves for momentum, energy, and continuity. And on the other hand, the magma ocean now is has very low viscosity, it's almost inviscid, it behaves like water, and therefore we have a huge range of a huge range of difference in viscosity, and we cannot solve in our model for that many orders of magnitude difference in viscosity, because the viscosity is related to the time steps in our model, or how quickly something moves. And then if the lowest time step would need to be for the magma ocean, we would actually not move anything in the solid. So this we cannot solve all at the same time, and so therefore we need to parameterize what is happening inside the magma ocean. And we can do that by assuming that the energy transport inside the magma ocean is enhanced. And so to do that, we determine the melt fraction inside the planet. And whenever we have melt, we artificially enhance the energy transport inside this magma ocean by assuming that now the thermal conductivity is extremely high. Because if we have a magma ocean, because the viscosity is so low, then the system would be vigorously convecting, so very efficient heat transport. And we can model this just by assuming that, okay, we have now a very high thermal conductivity. And so at the moment, this is like a first order approximation on how to deal with what happens when we have a magma ocean on our planet. And so I'm going to show you now just, this is a very early result on the interior dynamics of 55 Cancri, where now here we can see that we have a magma ocean. So the contour plot shows the melt fraction. So till here, we have a magma ocean, at least on the day side, and no magma ocean on the night side initially. And then, so what happens in this case now, so very quickly, the magma ocean grows and plumes and goes also towards the night side of the planet. And now plumes start to rise and then fuel a lot of energy inside this magma ocean. And the magma ocean, because of this very enhanced energy transport through the very large thermal conductivity, starts to equilibrate the temperature inside this planet. And so the temperature inside this magma ocean, so here in this region, we would have an adiabatic gradient of the temperature. And what we now see is just that we have the plumes that rise below this magma ocean. And what basically this does is that, well, we still have this large temperature contrast between the day side and the night side, but because heat is now redistributed so efficiently inside this magma ocean, the temperature here becomes like an average temperature, and below the solid mantle we'll just see like an isothermal temperature around this whole planet. So the solid mantle below will actually not see anymore this large temperature contrast between the day side and the night side. Yes, but this is a very early result, and we still need to improve the models. As you can see, it's still very slow, which has to do with like the magma ocean and the time stepping that we implement. So there's still much work to do on this part. So this is my summary slide for so for 55 for LHS 3844b, we have inferred two different tectonic regimes from the phase curve observations. The first one is a uniform distribution of upwellings and downwellings, And the second one is hemispheric tectonics, which is a tectonic regime that is currently absent in our own solar system. And so in the future, observations may possibly be able to distinguish between these different regimes. If, for example, we can link the regions here of the plumes to regions also of enhanced outgassing of volatiles, or to regions of enhanced volcanic activity. And then I've also briefly discussed the case of a hotter super Earth such as 55 Cancri, where we have seen that now, since the planet is much hotter, we could have a magma ocean on this planet, which could then equilibrate temperatures, which will then equilibrate the temperature between the interface between the magma ocean and the solid mantle. And so this would then make hemispheric tectonics, for this case, probably less likely. And with this, I thank you very much, and I'm happy to take any questions.
Great. Thank you so much, Tobias. That was a great talk. So yeah, if anyone has any questions, please raise your hand. While we're waiting for others to raise their hands, I think I'll take the first question. I was a little bit surprised on the first part on LHS, when you had the high internal heating, there wasn't any downwelling on the night side. I was just wondering if you could elaborate a little bit more, because I thought there would be a higher temperature difference there. So I would just naively think that there would be more downwelling happening on that side.
So you mean?
Yes.
The case with, well, there is when we have the weak lithosphere, right?
Right. I think it was the strong.
And then for the strong one. So why we don't have downwellings on the night side, you mean?
Yeah, is it just a factor of that lithosphere being just too strong to?
Yeah, I think that's the case actually in this case again, because the temperature is quite high, and inside the mantle, and then on the night side, because I mean the lithosphere is now strong. We don't vary the strength of the lithosphere as a function of the longitude. So the lithosphere has the same strength on both sides. But what we think is happening is that because the temperature on the day side is hotter, and so viscosity is also lower, so this might actually enable, so this might have a weakening effect on the lithosphere and then promote downwellings. And once this regime established, then we will have like the lithosphere from the night side, which will again just move from the night side towards the day side. But yeah, I mean, it's definitely not, I guess it's difficult to explain just by a simple like scaling relation or something, why exactly this is happening, because there are so many parameters, or there's so many things that we have to consider when we look at what promotes these downwellings and upwellings. And yeah, possibly the temperature on the day side could have an effect, a weakening effect, I guess.
Gotcha. That's cool. And before we jump to probable, someone in the chat, Brendan, asked what the difference is between the weak and strong lithosphere. Is that just the yield strength, the only difference there?
Yes, exactly. Okay. Yeah. So for a strong lithosphere, we assume a very high yield stress. So it takes stronger stresses to actually reduce the viscosity in this case. And when we have a weak lithosphere, in this case, the yield stress is quite low. And so when the stresses, as soon as they exceed this yield stress, we can promote the downwellings.
Gotcha. Cool. Prabal, do you want to go ahead?
Sure. Great talk, Tobias. Really interesting planets too, that, I'm excited about. So it's cool to see some of these models. I had a quick question on how you set these models up. So you might have mentioned this. How do you initiate your models? Do you assume, do you just have these initial conditions based upon present day scenarios? Have you tried to test if they were hotter or, different types of, scenarios?
Yeah, we didn't really assume different kinds of initial conditions. What we usually assume is that, especially for the case of LHS 3844b, there is some assumptions that we can make for what the temperature at the core mantle boundary could be, which, depending on what calculations one does, these might be quite high. And in this case, we made sure that we don't have a magma ocean, right, a basal magma ocean at the bottom of, so at the bottom of the mantle in this case. And then from that, we usually, we look what an adiabatic temperature profile would look like, and then take a reasonable temperature gradient. Well, we start from the surface, from the thermal phase curve, right? So from there, we then take a reasonable temperature gradient inside the mantle for the thermal boundary at the top and the bottom. But yeah, it's true. I mean, we could look at what it looks like if we take the different initial conditions. But the thing is, I guess we also assume that if the mantle is, if we set up the initial condition too hot, because of the viscosity effect on temperature and everything, the system would stabilize, would like tend to cool down. And if it's too cool, especially with internal heating again, then the system would the temperature in the mantle would increase and stabilize itself. So.
Gotcha. I have another question, but I'll wait for other folks first.
Great. Vlad, do you want to go ahead?
Yes, hello. Thanks for a great talk. I have a couple of questions. The first one is about the resolution of your simulations, and so whether the numerical viscosity is lower than the physical viscosity in your model. So that and the second question about the do we have any constraints on the Rayleigh number? I mean, so and how well can we resolve the structures? Because I see that the structures in your model are pretty large scale. So I just was wondering whether the effect of smaller vortices play any role in dynamics.
Yeah, thanks for the question. For the resolution, I think the models are run, so they are 2D models. I think we have run 512 to 256, so 256 grid cells in the C direction, and then 512 in the radial direction. About the numerical and physical viscosity, I have to say I've never looked at that. If they could be higher or lower, I don't know about that.
Well, the one suggestion I will make that if you can, change your resolution of your simulations by a factor of 2, let's say, and see if you get the same results, so that your
I think we
resolution.
Yeah, I think we have run, especially initially when we started the models. I guess we did run models with, like, starting with 64, 128, and then 128 to 256. And I think we have seen the same structures, or at least the same behavior. Although I have to say I didn't look really at the scale of the downwellings or upwellings in this case. So I guess especially for this case here, this could be interesting to look at, yeah, because here we have very narrow structures. So I guess it could maybe have a resolution effect in this case.
Thank you.
Thank you.
All right, Avi.
Yeah, it was just great talk, by the way. Really interesting.
Thank you.
I agree. These planets are high value targets, and it'd be great to see some predictions. I was confused about the. I mentioned this sort of up in the Slack, but for I think it was your strong lithosphere with basal heating, you had a time scale that was like 70 gigayears. And what it looked like was that for the first 5 gigayears or so, things were sort of unequilibrated or something
Yeah,
like that.
yeah, definitely.
So obviously, we're still probably within the first 5 to 10 gigayears of the planet's lifetime. So does that mean we're still in it? The planet would still be sort of in this unequilibrated state, or I mean, what does that mean for what we would actually detect for today?
Yeah, this is a very good question. Yeah, because I mean, yeah, obviously we run the models to 70 gigayears or so, which is obviously like much more than the lifetime of our universe. But the thing is, because for these planets, viscosity is so high, that this changes the time scales, and so therefore we will adapt our time stepping. And in our case, so this now falls back also to the question about the initial condition, because we need a little bit of time to just make the system equilibrate and then go into a state near steady state or something. And then we run these models for much longer because we are mostly interested in the statistical behavior of what happens now to the plumes and the downwellings. And so in this case, for us, it doesn't, yeah, we just run them for so long to really see, would it matter if after 20 gigayears, the system would completely change? And then again, but what we see is that this system seems to be quite stable. And the initial condition, yeah, in this case, is just we need to run it for that time to make the system to become stable, because probably our initial condition isn't exactly what, but we're not interested in this, or at least in this study, what the initial evolution of the planet would look like. Yeah, for this, I guess we would need much more like constraints, like how really the initial profile would look like and things like that.
Yeah, I guess I mean, it kind of points to that question though, which is, would the actual real conditions be very dependent on the initial accretion history of the planet if the equilibration timescale is so long? That means you're very obviously one conclusion might be that it'd be very sensitive to the initial accretion history, or whatever the history that led to the internal heat and structure of the planet at the initial condition. I guess that's what I was kind of asking.
Yeah, I guess it could. I guess this is true. Yeah, it could mean that this depends a lot on this. Well, yeah, especially for the question, what is the internal heating budget of the planet? I mean, in this case, we assumed something that is more or less Earth-like scaled to the planet, but obviously for this we would need much more constraints, also on the planet, on the host stars composition and things like that, which would then define the planet's initial internal heating budget. Yeah. So I guess, yeah, for further studies, this could definitely be looked into. What could be the effect of when someone assumes different conditions like that. Yeah.
Okay, great. Thank you.
Thank you.
Just to kind of build off of that, not to stay in this question too long, but I was just curious, like, could you imagine a scenario where you have an initial condition much more like your internal heating, and then the planet would evolve into something that has less internal heating? Like if you're considering strong radiogenics early on in a planet's history, like from aluminum or something like that, and then once those die down, it goes into a much slower state. So do you think that initial calibration to those initial conditions could happen much quicker, and then it transitions into a phase where the evolution is occurring a lot slower, like this example? If that makes sense.
So I'm not sure what you mean by could this transition happen much slower,
like that the whole initialization to the initial conditions, could that be happening in a world that is just hotter in the interior due to the accretion and due to just stronger radiogenics, so that things are happening much quicker? And then as the world cools down, then it can go into this more slower state like you're seeing here.
Yeah, I guess so. Yeah, this definitely be, I mean, as we see, yeah, for when we have the cases with mixed heating, now the timescales are much shorter. And so yeah, I guess a mix between these cases would definitely be interesting, because at the moment we just assume that the internal heating budget remains constant over time to just see what the effects of those are, right? But yeah, you're right. I mean, in the end, I mean, the internal heating budget will go down. And so I guess at some point we could have initially like a system like this, and then after that it would only be, then this would determine like the new state or like initial profile, and from then on we could go only with only with a basally heated system. Yeah, so that would definitely be interesting to look at as well. Yeah.
Cool. And probably you had another question.
Yeah. And I mean, yeah, this kind of idea, I think we're on this question because it's a relevant and fascinating question, right? I mean, if you can even get a binary signal that, oh, these planets have volcanism on the night side, and that connects to a more energetic past. I mean, that's pretty cool, right? That's really tracing their evolution. I actually have another question on it, kind of related to this. So you have these great convection profiles, all this other really cool stuff in these models. Is it possible for you to take a look at these plumes or the convection that's going on and try to pull out magnetic fields that are generated, stuff that like Pete Driscoll has done and other folks?
Yeah, I don't know. We have never looked at the connection between our models and the generation of magnetic fields. And I have to say, I don't really know how this calculation would be done, but
there's some symbols.
I mean, yeah.
Pete Driscoll has a paper. There are a couple other folks, Joseph O'Rourke. But I mean, you have interesting data here that I think will have interesting potential observable. So
yeah, I guess that would definitely be something interesting, because obviously in the end we want to somehow find out whether we can detect or distinguish these different regimes. And well, we have looked at, like, yeah, as I've shown in the talk, like just from the heat flux alone, but this is not enough. And then I guess even just volcanic activity, this possibly could lead to something like a signal, or maybe like if we have outgassing on only one side of the planet or something like that. But maybe, yeah, as you say, if we could link this rather to something which is more observable, like a magnetic field or so, and then we could see the trace of this, then that would definitely be very cool. Yeah. Because in the end, yeah, we can run all these simulations, but finally we want to see if we can actually say something. Well, this is now really happening. Obviously, we use observations to start our simulations and then say something. But in the end, since we still have to vary so many parameters, we would like to say something in the end also, which one of these cases is more likely. And for this, we need observations again. So we need to find something that we can actually observe. Yeah.
Thanks, Wes.
Thank you.
All right. Does anyone else have any other questions for Tobias? If not, then I think we will end it here. Tobias, thank you again so much for talking to us today. It was a great talk. Hope to run into you again in the future.
Yeah, thanks a lot for inviting me.
All right. Well, and thank you everyone for stopping by. We'll talk to you all later. Take care.
Bye. Take care. Thanks.